An equivalence relation on a set A is a rule R is a subset of a times A that tells us when two elements are the same in some sense. For R to be an equivalence relation, it must satisfy three simple everyday-like conditions. Reflexive, every element is related to itself. Formally, for all in A comma A is in R, think of a group of friends. Each person is automatically in the same friend circle as themselves. Symmetric, if A is related to B, then B is related to A formally. For all of B in A comma B is in R implies B comma A is in R like a two-way street. If you can go from city X to city Y, you can also go back. Transitive, if A is related to B and B to C, then A is related to C formally. For all of B, C in A comma B is in R and B comma C is in R implies A comma C is in R. Imagine a family tree. If Alice is a sibling of Bob and Bob is a sibling of Carol, then Alice is a sibling of Carol. When all three hold, we can treat the relation as a way of grouping elements that behave the same. These examples illustrate how equivalence relations capture sameness under different lenses: arithmetic, textual, and structural. Congruence modulo n, on the set of integers z, define A is congruent to B modulo n if and only if n divides A minus B. This is reflexive because A minus A equals 0 is always divisible by n. Symmetric because if n divides A minus B then n divides B minus A, and transitive because if n divides A minus B and n divides B minus C then n divides A minus C. It groups numbers into remainders 0, 1, n minus 1. Equality of strings, consider all strings over the English alphabet. The relation has exactly the same characters in the same order is just ordinary equality. It is trivially reflexive, symmetric, and transitive, and each equivalence class contains exactly one string. Graph isomorphism, two graphs G and H are isomorphic, written G isomorphic to H, if there is a bijection between their vertex sets that preserves edges. Reflexivity holds because a graph is always isomorphic to itself via the identity map. Symmetry holds because the inverse of an isomorphism is also an isomorphism. Transitivity holds because the composition of two isomorphisms is again an isomorphism. All graphs that look the same up to renaming of vertices end up in the same class. Given an equivalence relation R on A and an element A in A, the equivalence class of A is the collection of everything that is equivalent to A. A sub R equals the set of X in a such that A comma X is in R. We often write A in brackets when the relation is clear from context. Some practical tips for constructing classes. Start with a single element and ask what does the definition of R say about things that must be related to it. Use the properties because R is symmetric and transitive. Any element you find in the class pulls in all of its partners as well. Avoid duplication. Once you have built a class, every element inside it will generate the same class, so you do not need to repeat work. Example for the modulo 3 relation on the integers, 4 in brackets equals the set of -5, -2, 1, 4, 7, 10, because each of those numbers leaves remainder 1 when divided by 3. Notation can be shortened further. The set of all distinct classes is denoted a /r or a /tilde. When an equivalence relation R groups the elements of it into classes, those classes never overlap and together they cover the whole set. Such a collection is called a partition of A. Formally, a family P equals the set of P sub 1, P sub 2, ... P sub k of non-empty subsets of A is a partition if and only if. The union from I equals 1 to k of P sub I equals, as every element belongs to at least one part. For all I not equal to j, P sub I intersect P sub j equals the empty set. Different parts are disjoint. The equivalence classes A in brackets are exactly the parts of the partition induced by R. In everyday language, imagine sorting a box of mixed socks into piles where each pile contains socks that are the same color and size. Every sock ends up in one pile, and no sock belongs to two piles. That sorting is a partition. Conversely, any partition determines an equivalence relation. Two elements are equivalent exactly when they land in the same part. Suppose we are given a partition script P equals the set containing P sub 1 through P sub m of a set A. To turn this into an equivalence relation R subscript P, we define open parenthesis x comma y close parenthesis belongs to R subscript P if and only if there exists I such that x belongs to P sub I and y belongs to P sub I. In words, x is related to y if they sit in the same block of the partition. This relation is automatically reflexive because each x lies in some block P sub I, so open parenthesis x comma x close parenthesis satisfies the condition. Symmetric, the definition treats x and y symmetrically. If they share a block, the reverse holds. Transitive, if x and y share a block and y and z share a possibly same block, then because blocks are disjoint, all three must be in the same block, giving open parenthesis x comma z close parenthesis. Thus, any partition gives a well-defined equivalence relation. Real-world picture, think of a school divided into classrooms, the partition. Two students are classmates, the relation, exactly when they sit in the same classroom. The construction is reversible, which leads to the next theorem. For any set A, the map phi from the set of equivalence relations on A to the set of partitions of A, defined by phi of R equals A over R, is a bijection. Its inverse sends a partition P to the relation R sub P defined by being in the same block.
Proof sketch.
Injectivity, if R1 not equal to R2, then there exists a pair A comma B that belongs to one relation but not the other. Consequently, the equivalence class of A under R1 differs from that under R2, so the families of classes A over R1 and A over R2 are different. Hence, phi never maps two distinct relations to the same partition. Surjectivity, take any partition P, build the relation R sub P as in the previous topic. By construction, the classes of R sub P are exactly the blocks of P. Thus, phi of R sub P equals P. Every partition therefore arises from some equivalence relation. Bijection, combining injectivity and surjectivity, shows phi is one-to-one and onto, establishing a perfect pairing between equivalence relations and partitions. The moral, thinking in terms of groups of alike things, partitions, is exactly the same as thinking in terms of a rule that says when two things are alike, equivalence relations. Counting how many different equivalence relations exist on a finite set A of size n is the same as counting how many partitions of an n-element set there are. These numbers are called Bell numbers, denoted B sub n. Bell numbers satisfy the recurrence B sub n plus 1 equals the sum from k equals 0 to n of n. Choose k times B sub k, with B sub 0 equals 1. The term n choose k times B sub k counts partitions, where a designated element forms a block of size k plus 1 together with k other chosen elements. The first few values are B sub 0 equals 1, B sub 1 equals 1, B sub 2 equals 2, B sub 3 equals 5, B sub 4 equals 15, B sub 5 equals 52, B sub 6 equals 203, B sub 7 equals 877, B sub 8 equals 4140, and so on. Example calculation. For a set of three people, the set containing Alice, Bob, and Carol, the five partitions and thus five equivalence relations, are first, the single block containing Alice, Bob, and Carol, meaning altogether; second, two blocks, one containing Alice and the other containing Bob and Carol; third, two blocks, one containing Bob and the other containing Alice and Carol; fourth, two blocks, one containing Carol and the other containing Alice and Bob; fifth, three separate blocks, each containing one of Alice, Bob, and Carol, meaning all separate. If you need the exact count for larger n, use the Bell triangle, also called Aitken's array, or look up tables. The growth is super exponential. Even for n equals 10, we have B sub 10 equals 115,975 different equivalence relations. These numbers are useful in combinatorics, probability, such as random partitions, and computer science for clustering algorithms. On the set of integers, define a tilde b if and only if a minus b is even. Show tilde is an equivalence relation. Reflexive, a minus a equals 0 is even, so a paired with a is in tilde. Symmetric, if a minus b is even, then b minus a equals negative a minus b, which is also even, so b paired with a is in tilde. Transitive, if a minus b and b minus c are even, then a minus b plus b minus c equals a minus c, which is even, giving a paired with c in tilde. Hence, tilde is an equivalence relation, and its equivalence classes are the even numbers and the odd numbers. Let A equal the set 1, 2, 3, 4, 5, 6 and define x related to y if and only if x is congruent to y modulo 3. List all equivalence classes. Remainder 0, the class of 3 contains 3 and 6, also the class of 6. Remainder 1, the class of 1 contains 1 and 4. Remainder 2, the class of 2 contains 2 and 5. The partition is the set containing the subsets 1 and 4, 2 and 5, 3 and 6. The set B containing a B, C, D is partitioned into the subsets A and B, C alone, and D alone. Write the equivalence relation R on B that corresponds to this partition. Two elements are related if and only if they lie in the same block. From the block containing A and B, A paired with a B paired with B, A paired with B, and B paired with A belong to R. From the block containing C, only C paired with C. From the block containing D, only D paired with D. So R equals the set consisting of A paired with A, B paired with B, C paired with C, D paired with D, A paired with B, and B paired with A.